Welcome, everybody, to another installment of Nano at Tech. As you know, Nano at Tech is a bi-monthly seminar series hosted by the Institute for Electronics and Nanotechnology at Georgia Tech and the Southeastern Nanotechnology Infrastructure Corridor, one of the sites of the NNCI program funded by the National Science Foundation. So now today I'm going to pass it off to Professor Asif Khan, who will introduce today's speaker.
All right, thanks so much for everyone for coming. So let me take this opportunity to introduce the speaker. So we are very glad to have Dr. Saima Siddiqui as our speaker today. Dr. Siddiqui is a postdoctoral associate at University of Illinois at Urbana-Champaign. She received her PhD in electrical engineering from MIT in 2018, and afterwards she was a postdoc at Argonne National Lab. Her research focus is on magnetics and spintronic devices. She explores novel physical phenomena in electron spin in quantum materials. And these days she has been focusing on using these material systems and devices for building Boolean and non-Boolean devices for next generation energy efficient computing. She has been selected as an EECS Rising Star, and also she received the Drive Postdoctoral Award in 2019. So with that, let's get started. So welcome, Dr. Siddiqui.
Thank you, Professor Khan, for a nice introduction and for inviting me to the Nanotechnology Seminar Series at Georgia Tech. I really appreciate the opportunity to present my research on such a big platform. Today, I'm going to talk about magnetic devices and how they can form the basic building blocks for computing, memory, and in-memory computation. Let me talk first about what motivates the scientists and engineers all over the world to explore the in-memory computing. Here I'm showing the architecture of modern computer, which is based on the von Neumann architecture, and where the memories and the processing unit are separated from each other. And whenever it does any computation, data need to be bring back and forth between the memory and the computer and the processing unit through this cache. Now, cache here is also another kind of memory with very fast response time. A huge amount of processing time and energy are lost during this data movement. We have this problem ever since the modern computer was invented, but we work around this problem by improving the performance of the transistors in the processing unit and also by improving the memories. But today, we are in the cognitive era. We are not just happy doing regular image processing with the computer, rather we want our computers to make the decisions or sort the images based on those image processing. Or in other words, we want something that is called artificial intelligence. Now, for traditional image processing, the operation required element-wise multiplication of an image with a known filter, then accumulate the total of those multiplication to get the output. Now here, filter is an ensemble of weights represented by this matrix of size R by S. And the image is also a matrix of size H by W. And after multiplication of these two matrices, the output image is also a matrix which we have to store in the memory. Now, for doing the classification, in a single layer, it requires multiplication of matrices which are even larger in size. And every time we need to call these filters, large matrix of filters and weights from the memory and store the output in the memory. So you can imagine the resistive losses in moving the data around. And here I'm showing a single layer. But doing the classification of an image with human level accuracy, it requires hundreds of such layers. So we need to find the solution of this data shuttling problem now. And naively, one way could be bringing the memory close to the processor, so there is less interconnect loss or processing inside the memory. The other solution is the processing inside the memory to completely eliminate the interconnect loss. The system that performs such layer-by-layer operation are usually called neural network because of its similarity with the neural system in the human brain. Now, in human brain, data storage and the processing units are co-located. so it performs the data classification task most efficiently. So for computation inside a memory will be the more elegant solution of the data shuttling problem. I'd like to mention here that I will focus on the deep neural network in my talk. There are other type of neural network like spiking neural network. For the deep neural network, if you're interested, and I will cover the deep neural network using the magnetic devices as a building block. If you're interested in some other materials or other kind of devices, I would highly recommend to look into the work of Professor Asif Khan for devices, Professor Shimeng Yu for the architectural level analysis, and also Professor Mukhopadhyay and Arijit Banerjee for architectural level analysis. So, okay, moving on, I'd like to show what a human brain actually looks like. Now, looking inside a human brain is composed of billions of unit cells called neuron. A single neuron is connected with thousands of other neurons through synapses. Now, the synapses store the weights like filter, as we have seen in the previous slide. Now, any signal coming from the previous neurons are multiplied by the weights stored in the synapses. The cell body then sum all the weight signal and send the output signal to the next neuron depending on the predefined threshold. This is an essential operation to limit the output signal. So a neural network has two basic operations. One is a linear operation of multiplication and accumulation. Then the other is nonlinear thresholding to converge any kind of problem. So to mimic this neural activity inside a memory and remove the data shuttling problem, it's possible to use Ohm's law for multiplication. Now here, the output will be the multiplication of the voltage times the conductances. And this conductances will be stored in the memory, which we will use the magnetic devices for. But this conductance and resistance need to be varied to adjust the weight of the filters. And this variable resistor is called the synaptic device. For accumulation of these currents, we can rely on the Kirchhoff's law so that the output current at the end of this column will be the sum of all the currents coming through the different branches. Now, if we expand the system, we can use this cross-point, and at the end, we will need this kind of nonlinear activation function generator to converge any kind of problem or doing the thresholding like the neuron. Now, if we expand the system, we can use this cross-point architecture instead of the von Neumann architecture and compute in the analog domain. So I think there's a delay between what I'm talking about and what I'm going through the slide advance. Anyway, so all these conductance elements will be the conductances. We want this. So for all this conductances element, we want a storage element for storing the weights in the filter, and it would be even more elegant if we can replace this activation function generator also with a similar kind of devices, so that all the computation will be happening in the analog domain without going to the digital domain at all. And the top part, which does all this multiplication, will be performing as a synapse in the human brain, and all these neuron activation functioning are happening like the neuron in the human brain. So since we're talking about memories to store the elements, and we need some non-volatile memories so that the storage, although the device is storing the data, it doesn't go away when we power off our devices. So there are many non-volatile memories available. I'm talking in this case the three particular ones other than the magnetic devices: the phase change memory and the resistive random access memory and conductive bridge random access memory. In a phase change memory, a chalcogenide glass is sandwiched between two electrodes. This chalcogenide glass can change between the crystalline and amorphous phase on heating and cooling. And such phase changes are introduced by passing a current through the material to heat it up. Now, information is stored in the phases of the active material. Crystalline or amorphous phases had different resistances, which correspond to the different logic states. Now, phase change memory has been extensively studied over the past years, and they can be produced in the industry as a like mass production. So the other kind of memory is the resistive random access memory, which is also a sandwich of two metal layers, but metal oxide is sandwiched in this case between the two metal layers. And when an electric field is introduced between these two metal layers, then there is a creation of oxygen vacancies, and these oxygen vacancies move around with this electric field, resulting in the formation of a conductive filament in the oxide. And this changes the device resistance, which varies between the high and the low states. Now, resistive random access memory is a very promising non-volatile memory because of its uses, because of the materials they are using is also very common in the semiconductor manufacturing. Typically, the metal oxides includes hafnium oxide, tantalum oxide, titanium oxide, and aluminum oxide, all of which can be deposited using the atomic layer deposition. But however, because of the stability of this oxygen vacancies in these materials inside these oxides, the resistance are generated are not very reliable and are not very reproducible from cycle to cycle. And next, the other memory I want to talk about is the conductive bridge random access memory, which is similar to resistive random access memory. But here, the metal oxide is replaced by a solid electrolyte, and one of the electrode is a metal that can easily oxidize into the metal ions. So when an electric field is applied between the two electrodes, mobile metal ions from the top electrode migrate into the solid electrolyte to form a conductive filament that bridges the bottom electrode. And one of the critical issues of the conductive bridge random access memory is, though, the stochastic migration process. Therefore, the configuration of the conductive filament changes every time and as it reforms, and that results in a large variation in resistance change. There are other kind of memories like ferroelectric memories, which is also a very promising solution for being a non-volatile memory. But I will move on to the main topic I'm going to talk about today is the magnetic non-volatile memory. So the magnetic non-volatile memory is mainly an element of which is called magnetic tunnel junction. The magnetic tunnel junction is a ensemble of two ferromagnetic layers separated by an insulating layer. And whenever these two ferromagnetic layers have the same orientation of the spins in the two layers, therefore the density of states at the Fermi level align, and so that all the spins have equal probability of tunneling through this oxide to the other side, so which causes a low resistance state. So since this is a magnetic material, the density of the states of the both, say, up spin and down spins are not same at the Fermi level. So there are different density of states of, say, down spin compared to the up spin. And on the other side, if it's same, then the probability of tunneling is higher. But in case if they're reversed, one of the ferromagnetic layer is reversed, then this is now a high resistance state because now the spins at the Fermi level, the density of states of two different spins at the Fermi level are not same. So the tunneling probability is now lower. So it has a high resistance state. And the figure of merit for this magnetic tunnel junction is the tunnel magnitude resistance, which is usually represented by the change in the resistance of those two resistance states compared to its low resistance state. And this magnetic tunnel junction is the core of any magnetic random access memory. So in this slide, I'd like to convince you that why magnetic random access memory are more promising than the other options I have shown today. So here I'm showing the right energy for our memories right smaller. So the preferred position in this part is the bottom left. So if you look into all these different options and see these magnetic tunnel junctions or magnetic random access memory are represented by this green diamond, and they are more towards the preferred corner of all the other memories. So then in low switching time, energy. But if you also look into the programming energy versus the cell area, so programming energy is the same as what are on the right plot, and this energy is the same, but on the horizontal axis, I'm showing the cell area. And again, in this case, the magnetic tunnel junction memory, which are represented by this green diamond, has shown that they are one of the smallest cell size. They have one of the smallest cell size possible. And one of the other more important thing for the technology is that these magnetic tunnel junctions are relatively mature technology, so they can be easily incorporated into the industry or into the manufacturing. So this is my today's talk. I'm going to show you how we can use the magnetic tunnel junctions or magnetic devices to create an analog kind of devices to store the synaptic weights, and also use the similar devices for getting a thresholding device. And in the second part of my talk, I will talk about how we can create the digitized version of these synaptic and thresholding devices. And then the last part of my talk today, I'm going to show you how we can design a system with the analog devices I will show you in the first place. The analog devices. So before going to talk about the analog devices, let me show you one device which we use for storing. Actually, we use for a non-volatile device to create a logic performance. So this is a three-terminal device, and we can apply the input and input current between these two terminals. And we introduce a magnetic domain wall in the free layer where the magnetization changes in the magnetic tunnel junction. So this is the center part is the magnetic tunnel junctions, and where I have a fixed layer of ferromagnetic orientation here, but I introduce a domain wall in the free layer. So domain wall is just a boundary between two domains in the magnetic layer. And in this position of the domain wall, when it's left of this tunnel junction, then this is in a parallel state. So now the output resistance is low, or if I pass the current through this terminal, then the output current will be high. So this is a logic device, so it represents bit 1. Now, if I apply current, I can move this domain wall on the right side of this tunnel junction. Now I have a opposite orientation of this two ferromagnetic layer in this magnetic tunnel junction. Now the output resistance is high, so my output current will be low. So this represents bit 0. So I fabricated this device, and in this case, these three-terminal devices, these two terminals are represented by this two terminal, and the tunnel junction is under this middle terminal. And the wire in this cartoon image is actually designed as a semicircular arc because this helps us to get this domain wall with simply applying a magnetic field. Now, we start with the domain wall on the left, and it is in the parallel state. So the initial resistance is low. Now, if you apply a current pulse, which is about 1 microsecond, and this domain wall moves on the other side, now we have this opposite orientation. And we see that we can read that by electrically reading the resistance of this junction, and see that after a certain threshold voltage, the output resistance changes. So in other words, if you think that when our voltage is low, my output resistance is low. When my voltage is high, my output resistance is high. So this is an inverter operation of logic. So, and this device can be expanded to create even NAND or NOR operation by adjusting the width of the wire and by creating multiple input terminals instead of a single terminal. So now we know that these magnetic devices can create this kind of logic operations. So we sort of shown that the magnetic memories are good for creating logic operations. So now the question is, in this case, we have only two resistance states. So how we can use these devices to replace these conductances in the synaptic devices. So for that, we need to look into what's what are the requirements of the devices of the synaptic devices? The first one is the non-volatility. We know that we have that because it's a magnetic device, but we need also multiple resistance states, which we don't have yet. But also we have to have these resistance states linearly varying with the input current or input voltage. So here what we are going to propose. So here in this case, the magnetic domain wall, which can move in this wire, is not in the one side or the other side of the tunnel junction. Rather, this magnetic domain wall is under this tunnel junction. And with the application of the so now the output resistance would be now a combination of this, combination of this parallel resistance, which is when they are similar orientation, and the combination of this also anti-parallel resistance, where they are opposite in state, opposite orientation. And also it depends on where the domain wall is. Now, we know that the domain wall can be moved linearly can be moved linearly with an application of a current. So by using this equation, we can calculate the resistance can be also changed linearly by just moving the domain wall. So that's great. So we can replace this this synaptic devices with the magnetic tunnel junctions in the domain wall in there. So the question then is, what about this nonlinear activation function? Can we also replace that with the similar kind of devices? Again, if you look into the criteria, what we have to fulfill for the first one is non-volatility. We have that, but the multiple resistance state, we know how to generate the multiple resistance state. The question then is, in this case, the output resistance have to be changed non-linearly, and there are particular program that we should follow. There are particular kind of function we need to generate by using these thresholding devices. So here what we are proposing for that. So this is the same device, 3-terminal device. We have a magnetic domain wall in the free layer, and these are the 2 terminals where we apply current. And in this case, the resistance will also be defined by this position of the domain wall and how much area is parallel to the reference layer and how much area is anti-parallel to the reference layer. So if we have an input current of I in, then our resistance is defined by the same kind of resistance equation I showed in the previous slide. But in this case, we are changing the width of the bottom layer. Now, the domain wall, when I talk about the domain wall moves linearly, it depends. If you have the same current density along the length of the wire, then it moves linearly. Now, by varying the width of the bottom layer under this free layer, we are changing the current density constantly, and depending on where the domain wall is, it will every time see a different current density. So it will not move with this constant velocity. So we come up with this equation, analytical equation, and we can come up with what kind of width function we need to, what kind of width we need to actually create in our fabricated device to get a particular kind of non-linearity with the input. So in this case, the input is our current, the input current, and the output is the position of the domain wall. We can use this analytical function to create this kind of nonlinear width along the length of the wire. So we say, for example, we follow a nonlinear function of sigmoid, which is a very popular function in the deep neural network community. So we try to generate that, and from the analytical model, we know that we can generate that. But also with the micromagnetic simulation, we can come up with the width function so that we have this, we can get this kind of circles from our simulation that follows the sigmoid functionality. So we want to see the results in the experiment, not just with simulation. So what we have here on the right side, you can see that this is an image. This is an optical image, but it also can read the. So this is a this is a magneto-optic car microscope image. So in addition to this, seeing this device, we also can see what's the magnetic orientation of the ferromagnetic layer in this case. So the gray region here, you can see that this gray region shows one kind of domain, and the green region shows another kind of domain. So if you think that the gray region shows the up domain, then the green region shows the down domain. And the wire, you can see that I have a constant width wire, which is the width of the ferromagnetic layer. On the bottom, I have a platinum layer, which I shaped as we can estimate from our analytical model that what kind of shape the bottom ferromagnetic wire should be to get a sigmoid function. And we apply the pulse current along between these two terminals. And we see that the domain wall moves, and the position of the domain wall change actually as like the sigmoid function as we expected from our analytical model. So this is a very exciting result that we not only can generate the linear functions of the domain wall motion, but also we can program it in a nonlinear fashion too. So to summarize the first part of my talk, I have shown you that we can use this domain wall in a magnetic tunnel junction to create this kind of linear resistance change like in a filter. And we have also can generate this kind of nonlinear motion of those domain walls by designing the wire where we're changing constantly along the length. Now, to move on to the second part of my talk, I'm going to show you how we can use these devices for create a digitized version of those synaptic and thresholding device. So for that, we designed our magnetic tunnel junctions, and this is a magnetic tunnel junctions with the material is the ferromagnetic material is cobalt iron boron, and the insulating layer is the magnesium oxide. And we put a reference layer, which is a complicated antiferromagnetic layer on the top to create this reference layer hard enough so that it doesn't switches very easily with the application of the current. So we can see that we can generate by our magnetic characterization, we can generate different kind of domain orientation in the different magnetic layers. I'm not going to into the detail of that. Let me show you the device we designed after the. So we deposited all this thin film, and then afterwards we actually fabricated a device of this magnetic tunnel junction with all this reference layer. This is the reference layer, and we want to put our domain wall in these free layers. But first we characterize the tunnel magnetoresistance, which is one of the crucial figure of merit for the magnetic tunnel junctions. And we see that we have these two distinct resistance layer for regular ferromagnetic layer. Ferromagnetic magnetic tunnel junctions, which is defined the high resistance state is the anti-parallel resistance state, the low resistance state is the parallel resistance state, and in this case the TMR is about 44%. So then we actually designed we actually created a way to create the magnetic domain walls in this particular layer. So what we have to do, we apply only a small bias field that creates this two magnetic domain wall in this free layer, because now this high, the region which is outside this reference layer, that switches easily with the ferromagnetic layer, but the region which is inside this reference layer doesn't switches with this small ferromagnetic layer. So that creates two different boundaries on those edges, and these are the domain walls. So what we did, we apply to measure this the devices. We have created this kind of measurement scheme where we apply current, and this current, the amplitude of this current increases with time, and the pulses with the pulse width is always same, and the pulse width is usually in the nanosecond range, and there is a long wait between these pulses to measure the resistances after each pulses. And by using this scheme, we measure a device where, in this case, we want to create this synaptic device to create this with this multiple tunnel junction. So in this device, we have 9 magnetic tunnel junctions. So at the edge of this tunnel junction, you can see on the right that at the edge of this tunnel junction, that there is a magnetic domain walls each at each of these edges. And we have 9 of them. So at this in total, we have 18 domain walls in this device. But in this case, the width of the wire is not constant. The width of the wire is now linearly varying along the length of the wire. And on the bottom, I'm showing you the top ACM view. On the top left, I'm showing you the cartoon image and where the domain walls will. So now we have a magnetic tunnel junction, so we can read the resistance instead of just looking into the position of the domain wall. So when we apply a current, and we see that so in this case, we're increasing the amount of current. With the small amount of current, we see that the first domain wall moves, and we can read the resistance state on our measurement. And when we increase the current, the second domain wall moves, and we can see another step on our measurement. So this way, we can actually keep increasing the current, and we can see all the different resistance steps because of the motion of the domain wall. Now, if we look into this plot on the right, then we can see that it can be easily fitted with a linear curve, and we can change the resistance of this device linearly. One of the things to note here, in this case, we have 9 different magnetic tunnel junctions on the bottom, but we only can see 7 steps. So if all the devices, so in this case, all the devices did not switch. So all the devices did not switch. Rather, the 2 devices, the 2 tunnel junctions, which are at the end of this, which are at the thicker part of the wire, actually did not switch because the amount of current density needed to switch them is higher, so that is very high, so that can even damage the smaller region of the wire. So to show you the summary, that I have shown that we can create this kind of digitized version of the synaptic devices, which the resistance changes linearly, which is one of the advantage of this kind of domain wall devices, and are not very, this kind of linearity have not seen in any other kind of non-volatile devices. Then the question is, again, going to the activation function devices, and in this case, all sigmoid function as an example. And for designing this sigmoid functionality with these magnetic tunnel junctions, we have this wire where the width of the wire in this case also changes linearly along the length, but now the size of the magnetic tunnel junctions are varying along the length of the wire. So at the end of this so if we analytically plot what the function we want to see, then the small resistance step are coming from the small tunnel junction at the 2 ends, but the big resistance state are coming from the big tunnel junctions in the middle. And this is just analytically what we are going to expect. And this functions on the right shows very different on the left plot. This is because just a mirror, I'm showing here the mirrored version of the sigmoid. So we can create both the mirror or the actual sigmoid function. It depends on which kind of reference state we are going to start with the reference layer. So we use the same measurement scheme on these devices to read the resistances, and by measuring the 75 devices we can show that all of them are showing this kind of sigmoid functionality of those that we are designed this device for. And they are very well fitted with the sigmoid, the mirrored sigmoid function that we wanted to generate. So to summarize the second part of my talk, I have shown both the linear synaptic devices and the nonlinear activation function. Both can be generated in the digitized form with this magnetic tunnel junction. Now, the first motivation when I started talking about that this is the energy consumption of this of the devices, or we want to reduce the data shuttling. But the question now there is, if we want to measure, if we want to compute with this kind of devices, then what's the power consumption of these devices? So for the prototype devices, the power required to switch the magnetic tunnel junctions is roughly microwatt to milliwatt. But the current pulses we used is only 8 nanoseconds. So that means the energy consumption can be translated only to picojoule. And this is similar to resistive RAM, one of the smallest power consumption needed in any kind of non-volatile memories. Now, it's not fair to compare the prototype devices with the resistive RAM because resistive RAMs are always very skilled device. So I'm here going to give you some numbers which are taken from the industrial version of the devices. So it's possible to create magnetic tunnel junctions with only 20 nanometer in size, and the width of the cobalt iron boron or the ferromagnetic layer can be possible to narrow as 25 nanometer. And I'm here computing with a very conservative way, so I assume the current pulse is 8 nanoseconds, but it's possible to even switch these domain walls with current pulse as small as 1 nanosecond. Excuse me. So the energy consumption for these skilled devices would be in the order of femtojoule. Now, to give you an understanding that how small this femtojoule is, a biological synapse, which is the ultimate goal of our device community to get to, like in terms of energy consumption, these biological synapses are also switches with only femtosecond energy. Okay, so to move on, I have shown you this analog type of devices in the beginning and the first part of my talk. Now I'm going to show you how we can design a system with these analog devices. Now, to give you a brief review that these are the analog devices where the domain wall is under the magnetic tunnel junctions, a single domain wall is under the magnetic tunnel junctions to create, and by designing the wire, we can create this linear and nonlinear functionality. So to create a system, we want to do multiplication and then the thresholding. That's very simple. We have this magnetic devices at each of this cross point, and at the end of each column we have this thresholding devices, and that creates a weighted summation very easily. Now we also need to change the weights of this wire, so we need to able to select these devices individually. So for that we need switches, and in this case we will use transistors as our switch. And also to separate those thresholding devices from switching itself when we are switching the weights, so we also need the switches to separate these thresholding devices. Now to change the now to update the weights, we only need to connect these devices individually, and we can actually and we need to apply current to through this wire on the bottom wire. So if we connect this wire and not the crosspoint architecture, so we can change the width, change the position of the domain wall, and at the same time we can change actually different columns, but not all the rows together. Then we can read them to understand if this is really change or not, to verify the resistance change. And this is the whole architecture of a single layer for the deep neural network. The best part of this design is that when we are going from one layer to the next layer, usually for any other non-volatile devices, since there is no programmable non-linearity in those kind of non-volatile device, the signal in the analog domain needs to go to the digital domain and then back to the analog domain on the next layer. But with these devices, I have shown the thresholding devices, we don't need to go through the ADC converter or DAC converter between layer to layer. So there is direct connection between the layers, which can speed up any calculation of the deep neural network or deep convolutional network. In architectural point of view, it's simple and it's similar to the resistive random access memory, but the main difference again is there is no ADC or DAC between these each layers. But in terms of architecture, it's just there are voltage drivers and the crosspoint architecture in the middle, and then again sense amplifier at the end for each of these different areas. And they can be used to store different layers, or they can be used to store one single layer and separate them into multiple layers depending on the size of the neural network we need to implement. The key benefit of this kind of design, the architecture is it's that Since we are talking about multiple resistance states, the accuracy level can be improved even 20%. And also the neural network can be trained to optimize the process if there is any kind of resistance change because of the process variation of those magnetic tunnel junctions. And again, there is no extra storage overhead needed because of these non-volatile devices or magnetic thresholding magnetic tunnel junctions. And we have simulated only a very small 2x2 array of this magnetic tunnel junction devices, and we have seen that it only takes about only a smaller than the energy requirement for these devices are 5 times smaller than any other non-volatile devices. And in this case, we assume a latency of 4 nanoseconds in each of those layers. To talk about the future directions, I like to say that in future, what we want to introduce these devices in the back end of the processing unit, and the switches will be at the bottom, which are the CMOS switches in the first layer. And between these interconnect there, we can introduce these magnetic tunnel junction devices, which are the synaptic and the thresholding devices. What we are working on right now is we are trying to use, instead of these three-dimensional materials, we are working towards creating this kind of we are planning to use the two-dimensional materials, which will not only able to create this kind of deep neural network on the traditional sense, but all they can be easily incorporated into the flexible IoT devices to create the computation, to keep the computation local to those devices, or in other words, some smart IoT devices. To summarize my talk today, I have shown today is the design of the analog thresholding devices, and also I have shown that the digitized version of this thresholding device is the magnetic tunnel junction. And I have shown a nonlinear thresholding function devices, which is not possible with any other non-volatile memory options, and also shown you the architectural implementation of those devices in the system. I'd like to thank, so this work I have shown you today is done at my grad school at MIT. So I'd like to thank all my PIs, especially Mark, Caroline, and Lucia, who are really supporting me during this work and also supporting me during my grad school. And I also like to thank all of my colleagues. And at the end, I'd like to thank my postdoctoral advisor, who is supporting me through this postdoctoral analysis. And with him, I'm working on this implementation of this two-dimensional materials into these devices, see how well they can perform over the three-dimensional devices. With that, I'd like to thank you for listening.
Okay, I think you just, well, at least on my end, you froze a little bit there, so I missed the last couple of seconds of what you said, but I think you're ready for questions?
Yes.
Okay, great. So we do have a question in the chat, and feel free to add others if people want. So this question is from Hossein, who asks, what is the typical size of the domain wall, and how does it affect the size of a unit cell you can make, especially for the case where you are counting on having a splitted domain under the reference magnet?
That's a very good question. Thank you, Hossein, for asking. So the domain wall size, the material, it depends on the anisotropy of the materials. So depending on the anisotropy, the domain wall size can be as narrow as 5 nanometer. So when I'm talking about 20 nanometer in size, it's positive nanometer domain wall. And to have 20 nanometer magnetic tunnel junctions and assume that they're separated also by 20 nanometer, fairly doable. But I think the ultimate goal for us is to create a long tunnel junction rather than that can control even well. The resolution of those resistance will be even higher, so that we can even create multiple steps in the complete analog device.
Great, thank you. Asif, did you have any questions?
Yeah, so this is a great talk, Dr. Siddiqui. So I have a couple of questions. So first thing that comes to my mind is that right now, so I would say that the STT-MRAM, right? They're probably the one of the few non-silicon devices that made into the industry right now, right? So for example, Intel, Samsung, TSMC, they're all offering STT-MRAMs and 22 nanometer node, right? So in that, from that perspective, right? So that actually means that the foundries will actually be open to introducing new materials and new kind of devices like you are doing on the domain wall based devices, right? So do you have any thoughts as to introduce this kind of structure? What might be the hurdles, or like how realistic it might be, or how realistic it might be that the new kind of devices, non-traditional spin devices, how easy it will be to introduce in the industry technology nodes.
Right. That's a very, very interesting question. So I will start with the hurdle. What are the challenges of the domain wall device? If you look into the image, the slide, this one.
Mm-hmm.
And when I'm moving this domain wall, and these are the measurements from 10, 15 cycles, and I plotted this average of those steps, right? Mm-hmm. The step height is not that different between one cycle to the other cycle. But if you look into the error bar along the x-axis, which is how much current I need every time to move the domain wall, they are kind of not very, the error bar is kind of very big. So sometimes particularly if you look into this one looks like sometimes I see instead of one movement, the two domain walls move at the same time. So it's there are some stochasticity in this kind of devices, and that I believe is one of the hard challenges we need to overcome. And this stochasticity is mainly coming from the domain wall movement are mainly coming from so when you apply the current, they have to thermally excite these domain walls, then they start moving. So we need to get rid of this kind of thermal excitation. So it's very well studied over multiple years how the domain wall moves. So in the ferromagnetic materials, it's not that easy. Then we can introduce some new other materials, say ferrimagnet or antiferromagnet materials, where this kind of movement should not be excited by this thermal excitation. So maybe that's one way to go. But then they are not coming free without challenge. Then there is a challenge of how you can detect the magnetic state in an antiferromagnet, how we differentiate between two different domains, and then getting the signal between these two different domains in the antiferromagnet the resolution is even lower. So there are some challenges in both ways. So I believe that's the main challenge, the stochasticity in these devices, for them to be rightly implemented in the device, in the technology.
So,
but there are other. So yeah, go ahead.
Yeah. So materials-wise, right? So materials-wise, what are the materials that you're using? Like all the different kind of materials that you're using for your domain wall devices or magnetic tunnel junction devices. What are all the different kind of materials that you're using? Like for example, you're using PB and.
Sure. Let me. So the device I've shown you here today, this is the stack I was using, where there are cobalt boron and also the cobalt platinum multilayer to create a synthetic antiferromagnet. So the reference layer is actually this.
So did you actually make this device in your lab?
Yes. Yes.
All right. So this is like, and so like all these materials are already introduced in the fab, right?
Yep, I believe so.
So, all right. So that means that to make your devices, you don't need to introduce any new devices. So that's great, right? So that's why basically it will work on an industrial platform. So the second question is, do you have any comments on the scalability? Because it seemed like your devices are like micron scale long, and MTJ I believe is like in 22 nanometers. So probably the size of these devices are 50 nanometer by 50 nanometer. The MTJs that they have there. So the area footprint is of the order of micron.
So for my device, yes, these are the prototype devices. We did not take we did not take chances to have those alignment issues in the E-beam or anything. So we directly started with, okay, we'll start with the size of the MTJ we are very comfortable with. So that's why the size of the MTJs are 200 nanometer. But even in the academic lab, designing a 50 nanometer MTJ is not impossible. We can do that. So it's possible to make these devices. So say I have shown 8 steps. So it's like 3-bit device. If I want to create this 3-bit device, it can definitely be possible to scale within 100 nanometer very easily.
All right, sounds good. So yeah, so you mentioned about the stochasticity, but the thing is that even if you can use a stochastic by itself, stochasticity is, and like, of course, from a memory perspective, we do want to get rid of the stochasticity, but again, we can use the stochasticity as a computational use at a computational block or something as well. So there are many applications for this.
We can use that as a like for probabilistic computing, definitely. But that will not be for deep neural network. That will be something else.
All right, sounds good. So there is another question from Hussein again. So go ahead.
Sure, I'll read it. So can you also comment on the deposition of these layers? Some of them are only a few angstroms, like that
Yeah. So I use sputter deposition, and with the control of power and with the control of where you're depositing in your sample, it's possible to control the thickness. So I believe, for say, if you assume have something less than 0.5 nanometer, like the tantalum layer between the cobalt iron boron and cobalt platinum multilayer in this one, so it's probably not a very continuous layer. But without this tantalum layer, you do not have the particular anisotropy in cobalt platinum. So although it has a sub-nanometer thickness, this is very important to get the right anisotropy in the different materials.
I think I'm going to say our time is up. And say thank you again. We very much appreciate you spending the time with us at Nano@Tech. And
yeah, thank you.
And thanks again.